Good day. I'm John Yembrick with NASA Public Affairs, and welcome to NASA's Ames Research Center here at Moffett Field, California. Today we're here to announce a new discovery for NASA's Kepler science mission. Joining us here today to discuss the discovery is Charlie Sobeck, Kepler Deputy Project Manager here at NASA Ames. Nick Gautier, Kepler Project Scientist from NASA's Jet Propulsion Laboratory. Laurance Doyle from the SETI Institute and the lead author of the paper that is being published today in Science. John Knoll, Visual Effects Supervisor with Industrial Light and Magic. And Greg Laughlin, Professor of Astrophysics and Planetary Science at the University of California, Santa Cruz. We'll start with some opening comments and then take questions here at Ames and on our phone bridge. Charlie?
Thank you, John. I'd like to welcome everybody here and thank you for coming. I think we have some really exciting news from the Kepler mission that we'd like to share with people today. I would like to, before I hand off to the rest of the panel here, give people a little bit of a background on to the Kepler mission. It was approved in 2001, launched in March of 2009. The development of the Kepler mission was managed by the Jet Propulsion Laboratory down in Pasadena. Ball Aerospace provided both the spacecraft and the science instrument. The mission science has been managed here at NASA's Ames Research Center, and Ames also has responsibility for managing the overall mission through its flight operations. We have here at Ames over 50 scientists and engineers whose job it is to oversee the mission and to deliver the data to the science community. We have a team that includes both civil servants and contractor employees that are refining and operating an automated data pipeline that sifts through that flight data and finds objects of interest. We have an on-site science staff which evaluates that data and ensures that it's coordinated and delivered to literally dozens of affiliated scientists around the country and around the world to produce really truly remarkable findings from this exciting mission. And with that said, I'm just going to give it to our project scientist, Nick Gautier, to describe a summary of what these exciting findings are for today. Nick?
Thanks, Charlie. I'm Nick Gautier at the Jet Propulsion Laboratory, and I'm the project scientist for Kepler. So we're here today to announce the discovery of the circumbinary planet Kepler-16b. Kepler-16b is called circumbinary because it orbits around a binary star. That's a pair of stars that are in orbit around each other. In the artist's conception, you see here, the two stars are the big yellow disk and the smaller red disk. The planet Kepler-16b is the small black disk just about to pass across the face of the red star. This is the first definitive detection of a circumbinary planet and is the best example we have of a Tatooine-like world from Star Wars. Now, we don't expect Luke Skywalker or anything else to be living on Kepler-16b, but if you could visit there, you would see a sky with two suns, just like Luke did. Before we get into the details of Kepler-16b, I want to tell you a little bit about the Kepler mission and how it finds planets so everybody will understand how we discovered Kepler-16b. Kepler is NASA's mission to take a census of planets around stars in the neighborhood of the Sun and to find out how many Earth-sized planets that might be habitable are out there. Kepler was launched in March of 2009 and is now in its third year of operation searching for exoplanets. Those are planets that are in orbits around stars beyond the Sun. Last February, we announced the discovery of 1,235 exoplanet candidates, many of them in systems of multiple planets, many near the size of the Earth, and many at a distance from their star that would give them a temperature that might make them habitable. At the time, 15 of those candidates had been confirmed as definitely real new planets. Since then, Kepler has been working hard on new discoveries. Many new candidates have been identified and are going to be announced next month. 5 more planets have been published and confirmed, and many more are on the verge of publication. Kepler-16b is at the head of the list of new planets to be published, making it the 21st confirmed Kepler planet. Now, let me explain a little bit about how Kepler finds planets. One way to find extrasolar planets is to find those stars whose planets have orbits that take them in front of the star as seen from the Earth. Then, once per orbit, the exoplanet will pass across or transit the face of the star and for a few hours block out some of the star's light. I have an animation to show you how this works. Kepler monitors the brightness of a star to make what we call a light curve, seen here at the bottom of the picture. The star's brightness is constant for most of the planet's orbit. Then, for a few hours, the planet transits the star and the light curve dips by a small amount as some of the star's light is blocked out by the planet. We can tell the size of the planet because we measure the size of the dip, and we have a pretty good idea of how big the star is. We know how far the planet is from its star because we measure the period of its orbit by the spacing of the dips in the light curve. Now, just like transiting planets, a fraction of binary stars also line up with the Earth to produce eclipses and generate dips in their light curve. These stars, called eclipsing binaries, are an important part of the story of Kepler-16b. Kepler is interested in finding planets around any star, but planets around binary stars are particularly interesting. For one thing, there are about as many binary stars as there are single stars. Laurance tells me there are over 2,000 eclipsing binaries in the Kepler field of view, so planets around binary stars could be very common. Also, planets around binary stars can tell us a lot about planetary system formation, because the gravitational field and the orbiting of the stars poses severe tests for theories of planet formation. For instance, will planets around binary stars tend to form in the same plane as the orbit of the stars, or can they be orbiting any which way around the stars? Planets around eclipsing binaries are more interesting yet, because with an eclipsing binary you can figure out the mass and size of the stars to a very high precision, and this nails down the size of the planet and the distance from the stars to much better than you can do with an ordinary single star. Last, I want to point out that finding transiting planets around eclipsing binaries is not as easy as finding transiting planets around single stars. The motion of the stars makes the transits non-periodic, so they're harder to sift out of the light curve. We expected we might find some circumbinary planets, but Dr. Laurance has done an amazing job to sort out Kepler-16b, and I now pass it to him to explain his discovery. Laurance?
Thank you, Nick. My name is Laurance Doyle, and I'm a principal investigator at the SETI Institute, and I'm a participating scientist with the Kepler mission. And what that means is that after the Kepler mission was funded, I wrote to NASA headquarters and said, I think circumbinary planets would be really neat to find. And they said, good idea, and sent money. So I'm kind of icing on the cake. You might say on the Kepler cake. So what did we discover? Well, let's watch a movie of that. This is the planet, Kepler-16b. It's about 1 Saturn mass, and it orbits with a 229-day period around 2 stars that are orbiting around each other. Now notice these 2 stars are eclipsing each other, and this is called an eclipsing binary. One's about 69% the mass of the Sun, and one's only 20%. What makes this remarkable, though, in that 41-day period, by the way, what makes this remarkable is the planet also transits both components. So that was a secondary transit followed by a primary transit. So in other words, we have 2 stars dancing around each other, and in our line of sight they eclipse each other. And then we have this exquisite little pirouette of the planet going around both of them, and we get to see how big the planet is as well. Here we have an explanation of what eclipsing binaries actually are. How they perform and how we know what they look like. A light curve is a plot of brightness with time. We see in the first frame the 2 stars are different brightnesses. In the second frame, the bright star is being blocked, and that causes a primary eclipse, which is the deepest dip that we see in the light curve. In the third frame, they're out of eclipse again. In the fourth frame, the fainter star is now blocked by the brighter star, and that's called a secondary eclipse. Well, you can see we can get the rotation period of the eclipsing binary by just measuring the separation of the 2 primary eclipses. And next. This is the actual light curve of Kepler-16b. The blue lines are the primary eclipses, and the yellow lines are the secondary eclipses. So you can see blue, yellow, blue, yellow, blue, yellow repeated. There's a little bit of missing data there. The spacecraft has to roll sometimes and lose data. But basically, this is an eclipsing binary we picked out of a light curve. But we notice there's something else going on here. Very interesting. See the little green? That's an extra feature. We call that a tertiary eclipse. because we didn't know if it was a star grazing the eclipsing binary or if it was a planet. But we got excited, and we saw another little dip that was much smaller, and that's red. You have to kind of squint to see it. We said to ourselves, now is this a background eclipsing binary that happened to get in the field of view of the foreground Kepler-16? Well, then what we saw is, you'll notice the second frame, the second square, the red dip leads the green dip. And then in the right square, the green dip goes first again. So they're switching places. Well, a background eclipsing binary doesn't turn around and go this way all of a sudden. Well, what else could explain that? Well, let's look at a little clip, a movie, and this will simulate, we have two stars of unequal brightness, unequal size, and we've taken out the eclipses. All we're going to do is look at the drops in brightness due to the actual planet. And I just want you to look at the top line. The planet went across both stars and it dipped, but notice the dip on the left is wider and shallower than the dip on the right. So now we're going to trace out, this top line is going to become the second line for comparison, and here's the dip. The top line is now the dips just made again. Notice now the deeper, wider dip is on the other side. That's because the planet went across the smaller star first. Now what happens if the star arrives when what happens when the planet arrives when both stars are together? Well, you get this really long extended dip. So basically what this is illustrating is how, not only how the Kepler-16 dips could change places, but that you can get a very complex quasi-periodic signal when you try and detect planet transits across stars that are actually moving while the planet transits. Next movie. Okay, here's a simulation of animation of Kepler-16b. And notice the third object is now closer to the yellow star. And now it's closer to the red star. Now it's closer again to the yellow star. Well, we wanted to see, is it a star that's causing the dips, or is it a planet? Well, one way we can tell is that the third body, every time it gets closer to the two components of the star, it gives them a tug. And that tug results in a change in the orbital period of the eclipse times. So we can actually time the eclipses and say, okay, are the eclipses being altered by another star, or are they being altered by just a little bit by a planet? So let's go to the next slide. Here's a plot of the eclipse timing on the left with time. In other words, over the days that we are examining this system, we actually looked at the time the eclipses occur. Now we can put a stellar mass in the system and say, okay, it's going to be doing the tugging. How much would it change the orbital period of the two stars? Well, by 200 minutes, plus or minus 200 minutes. And so the yellow curve illustrates, if it was a star, this is how much the eclipses would change. So let's go to a smaller mass. Next one. The green is actually if you had a brown dwarf. Now that's a failed star, and they're only about 13 to 70 times the mass of Jupiter. But nevertheless, this is how much it would deviate by plus or minus 40 minutes. Well, we didn't see that either. And next, so we put in a planet mass, and that's the blue line here. And let's look closer at that. We'll blow up this region. Now this is actual Kepler timing data, Kepler-16 time data, and the blue points are the actual data. What those data are the times that we recorded the eclipses happening. And so as we look, it is varying. So there's something there, but it's only varying by about a minute. You can see that the times are up above the dashed line and then below, up above, below, up above, below. And then the diamonds are our model. Well, the best fit of our model was for a one Saturn mass circumbinary planet. So this diagram, with this diagram, we knew we had nailed the first circumbinary planet. Next one. So in conclusion, here's our system. We have a Saturn mass circumbinary planet, half rock and half gas. It's in orbit around stars that are both smaller than the Sun. Here's the size of the Sun for comparison. It's the two stars are in an eccentric orbit around each other. The planet is in a nice smooth planar orbit, but you know, scientists like to find other examples of things. Like, for example, if we found evidence of life on Mars, we'd be able to calibrate life on Earth. Kepler's looking for other Earths. If we can find other Earths with Kepler, then we'll know where we stand as far as an Earth. Well, this is an example of another planetary system, a completely different type that we've never seen before. And so that's why everybody's making a big deal of it. Nobody's ever seen a place like this before, with one exception. I seem to remember seeing a place like this about 30 years ago in a galaxy far, far away. And so I'd like to introduce the people that had enough faith in circumbinary planets to put their hero of Star Wars on a circumbinary planet named Tatooine. And so one of these thought pioneers is with us today, and from Industrial Light and Magic, here's John Knoll.
Hi, I'm John Knoll. I'm a visual effects supervisor at Industrial Light and Magic. I supervise visual effects on 3 of the Star Wars pictures, and in each of these we depicted scenes that took place on a planet around a binary. So let's run the clip. So I'm here because Tatooine, a planet depicted in Star Wars as famously orbiting around a binary, was not known to actually be possible at the time. That when George Lucas was first writing that his hero was living on a planet around a binary, he was using a visual shorthand, a way of kind of wordlessly showing that we're not on Earth, that we're in this odd, exotic place. In the film, it comes at a time, a very emotional moment, and it's a very memorable scene as a result. And I don't think George particularly concerned himself that the leading theory of planet formation made this setting somewhat unlikely. But Kepler-16b is unambiguous and dramatic proof that planets do form around binaries. It's possible that there's a real Tatooine out there. A planet like that really could exist. I've been to the fictional Tatooine, and it's a very hot place, actually, by the way. And I got to be honest with you, it looks a lot like North Africa. But when I was a kid, I didn't really think it was going to be possible to ever be able to make discoveries like this. That I imagined that the distances were so great that the optical resolving power that was going to be required to be able to pick out a planet around a star was going to require infeasibly large instruments, or that to be able to detect a tiny point of light kind of staring right into the barrel of a star was going to require instrument sensitivities that I didn't think we were ever going to see. And I'm amazed that we've come up with these very clever techniques. The occultation method used by Kepler is just a great way of being able to extract this information in such a clever manner. And I can't help but think of the strange and exotic setting that a discovery like this suggests. As somebody who works in film, we're frequently called upon to depict something that's never been seen before, but again and again we see that the science is stranger and cooler than the fiction. So I and many of my colleagues take great inspiration from discoveries like this. And I know that George Lucas is a strong proponent of expanding the frontiers of knowledge and understanding. And there's no doubt that these discoveries influence other storytellers. And the very existence of these discoveries gives us cause to dream bigger, to question our assumptions, and to be open to new possibilities beyond what we think we know. And now to move away from fiction and back to the science, here's Greg.
Yeah, so my name is Greg Laughlin, and I'm a professor of astronomy and astrophysics at the University of California in Santa Cruz. And sort of coming here as an outside commentator, I really think I speak for everybody who's on the line and in the room, that it's been remarkable how the whole Kepler team and the Kepler satellite has brought these exotic environments that were once the realm of science fiction firmly into the realm of science fact. And this discovery of Kepler-16, in my view, is important for 3 different reasons. First is simply that the quality of the data that's coming from Kepler-16, the quality of the data that Kepler gets, that this system provides, really provides a jump forward in our ability, or in the Kepler team's ability, to probe the dynamics, to probe the physical conditions that exist on this system that's many light years away. To make an analogy, it's a bit like going from listening to one of your favorite pieces of music on a scratchy, noisy cell phone connection, and then going and actually hearing that music on a very high-end stereo. There's just this phenomenal increase in the quality that the Kepler mission is giving back with respect to extrasolar planets. And then another reason why this is important, if we go to this first slide, this is a picture of a newborn binary star called GG Tau, and it's surrounded by a disk of gas and dust. And this is an important environment because it's representative of literally billions of binary stars that are out there in the galaxy. And it's long been suspected that you can have planets that form in the circumbinary environment. And these disks which orbit the binary stars, and in this next slide there's an artist's impression that gives a little bit clearer sort of picture of what's going on here. In this disk surrounding the binary stars after the binary stars are born, it's been believed that planets can form there. But because the binary star provides gravitational perturbations and provides a complicated environment, there was no proof positive until now. And so now, with this discovery of the Kepler-16 system, we have both a beginning point that NASA missions like HST and Spitzer have provided. We see the initial conditions, and then with Kepler-16 we see an example, a beautiful example of the final outcome. And we know now that with very good likelihood systems like this are common throughout the galaxy and indeed throughout the universe. And the whole sort of idea of binary stars becomes very concrete when we think about the very nearest stellar system to our own sun. And this last slide, which I think is perhaps not that well known, but which I think is one of the most inspiring missions that NASA has ever, or one of the most inspiring pictures that NASA has ever taken, is from the Cassini orbiter, which is sort of humankind's far sentinel out in the Saturnian system. At one time the Saturn system was full of mystery and was on the horizon. Now we as a society are there, and this picture through Saturn's ring shows the Alpha Centauri AB binary pair out there 4.24 light years away, and we can't help but imagine what kinds of planets are orbiting the pair of those stars and those two stars individually. And I think that this discovery of Kepler-16 really points the way towards all of these amazing things that we're going to learn in the decades and years to come.
Thank you. We'll now take questions here at NASA's Ames Research Center and followed by our phone bridge. Please remember to wait for the microphone, state your full name and affiliation, and to whom your question is directed. We have a question over here in the front.
Hi. Let's see, Mike Wall from space.com. I guess this is just for the panel. I mean, this is the first one you guys have actually confirmed around a two-star system. Could you just say something about what does the actual theory say? Is it more likely that these planets will be rocky, or is it less likely that they'll be rocky? I mean, is it more or less likely, I suppose, that life could take root on a planet like this? I mean, around a two-star system than around a single-star system like we're used to dealing with, I suppose, is my question.
Greg, you want
to take a first shot at that?
Sure. So Kepler-16, it's important to know is sort of a Saturn mass, Saturn size planet. And so no one's expecting that there's going to be life on Kepler-16. It's much more important because it's a proof of principle and we're getting this beautiful data back from it. But the fact that it's there, the fact that you have a Saturn sized planet there, most theorists believe that in order to build up to a Saturn sized planet, you need to go through kind of a rocky, icy terrestrial phase first before you can accrete the full volume of gas and volatiles that you eventually get. And so the fact that you have this planet there, very clearly there, in my view, implies that it's much more likely that circumbinary terrestrial planets are going to exist. And what's exciting is that that's not some sort of big picture, long-term goal. That's something that Kepler, with its fantastic capabilities, especially if it can observe for a long enough period of time, will almost certainly find some of those systems. So I think that it's really pointing toward the fact that we can look forward to a number of great discoveries coming from this mission.
I just might add, too, that you usually think of the habitable zone as a shell, a sphere around a single star. Well, in this case, the habitable zone's moving as the two stars get closer and farther away from the planet. So the whole habitable zone is this big dynamic thing. The temperature on Kepler-16b can vary by 30 degrees just on the outside of the atmosphere, just due to the motion of the two stars. So this hab zone idea of being a place in the solar system has got to change. It's this dynamic thing now.
But I'll also just point out that we have 4 examples of gas giants in our solar system, all of which are outside the traditionally thought habitable zone. And there are a couple of very plausible life candidates in Enceladus and Europa. So the gas giants like Kepler-16b may in fact have moons around them that do have favorable conditions.
Lisa Krieger, the San Jose Mercury News. I wonder if you could just imagine yourself as a Luke Skywalker on this planet. What would it be like looking out? What would the length of day be? The sunrise, sunsets, shadows, things like that.
I could take a first crack. We don't know the rotation period, so we don't know about sunrise and sunset. But let's just say the sun is setting. The sunset would take place, sometimes the red star would set first, sometimes the orange star, sometimes they'd set touching each other, sometimes set together. So you get this very dynamic sunset. It's never 2 sunsets are the same. So that's, at least we know that far. You'd have, of course, 2 shadows, because the red star would fill in, the orange star would cast a shadow, but the red star would fill it in because it's at a different angular point in the sky, and vice versa. So, if you want to tell the time by sundial, you need calculus,
I think I could add a little bit to that. One very extraordinary thing about the data that Kepler returns is that once a system like this has been found, and once it's been monitored for a sufficiently long period of time, you know everything so that you can calculate. You can calculate exactly what the sunsets would look like, exactly what the sort of odd patterns would be, and using sort of the facilities that are used to make these highly realistic special effects, you could see exactly what it looks like.
I'm Jeff Scargill. I'm here in the Planetary Systems branch, the Space Science Division at Ames. I think this is a question for Greg. There was reference to the unlikelihood of this system as it was known many years ago. I'm remembering work done on the stability of orbits around binaries by Dave Black and Yvonne Pendleton. And so I know theoreticians are good at adapting to changing data, but can you just summarize what's changed about the theoretical ideas connected with orbit stability and that kind of thing?
So the question here is when you have a binary star with planets orbiting that, the binary star produces gravitational perturbations that can be very severe for planets. Planets can get tossed out of the system or tossed into one of the stars. But this particular planet is far enough out, it's far enough away from the 2 binary stars that it effectively is feeling them as a single gravitational attraction. And while there's perturbations, those perturbations aren't severe enough to actually cause problems for the orbit. And so I think that the fact that this planet is found in this orbit is exciting because it points to many more of these are likely coming down the line. But it's not surprising from a dynamical stability sense. I think that it's very clear that this planet should be able to orbit, not just for the time that it's been there, but for many billions of years to come without experiencing any significant difficulties.
I will say we ran the Kepler-16 system over several million years of orbits, and it was stable. There was no indication it was going to go unstable.
Question in the back.
Neil Heather from the SETI Institute. I was wondering why it's called 16b, and if it's going to be renamed at some point with a more sort of friendly name like one of our own planets in our own solar system, and who gets to name it?
Well, it's named Kepler-16b because the conventional way astronomers name planets is they take the name of the star and then they attach a lowercase letter to it starting with B. And if they find more planets around it, they'll use more letters. So the second one that Laurance is going to find, I'm sure, would be Kepler-16c, and so forth. Now, the question of whether it gets a more friendly name, it might be up to the press, who knows. But typically the International Astronomical Union will sanction official names, but they've already done that. Kepler-16b is the official sanctioned name. So I don't know, maybe it's up to the public and the press to give it a nickname.
Tatooine.
Well, as long as that's not copyrighted.
Thank you. I see more questions here at Ames. We'll go to our phone bridge.
Hey, this is Alan Boyle with MSNBC. I had a quick question, just whether this was found in Cygnus or Lyra, and then the other question would be whether the fact that this is a circumbinary system, are there special challenges for, say, finding Earth-like planets with smaller sizes or masses that are around circumbinaries, or is it the same challenge pretty much as finding an Earth-like planet around a single star? Thank you.
Okay. Well, if you want to find Kepler-16, it's 11.5 magnitude, which is, you could probably squint and see it through binoculars. So amateur astronomers out there, you can find Kepler-16b. The way you do it is, in Cygnus the Swan, the right wing, which is most west, which is next to, it's in the Vega direction. When you look up in the, when you look up in the summer triangle, you see 3 stars, and Kepler, the Cygnus the Swan has 3 stars in the right wing. There's a bright star in the middle called Iota 2 Cygni, which is 3rd magnitude. So if you can find that, you're within 1.5 degrees of Kepler-16b. Now I say, okay, why going through this whole description? Because next year, Kepler-16b will make a 1.7% drop in the brightness of the star Kepler-16 capital A. And that will be visible from China, India, Russia, Korea, and Japan, and so on. So if you're an amateur and you want to detect the first transit since the discovery of a circumbinary planet, you can go to the northeastern hemisphere of Earth, and 1 or 2% drop is something amateurs can do. So that's how to find it. What was the second part of your question?
About the challenge for finding smaller Earth-sized planets, whether it's more complicated for a circumbinary system than it is for a single-star system.
It's a little trickier because you get a quasi-periodic signal, and also the signal is a little dimmer because you have to deal with blocking out 2 stars. In other words, when the planet goes in front of one of the stars, you still have the brightness of the other star. So if it's 2 solar-type stars, you have to get more signal to see it. But I don't see any reason why a habitable planet could not form, now that we understand Kepler-16 a little better, in a circumbinary orbit. So I guess it's a little bit more difficult to detect, but once you detect it, you'd probably be able to characterize it a little bit better.
Thanks. Let's take our next question from the phone bridge.
Robert Lee Holtz at the Wall Street Journal. I have just a straightforward question. How many light years from our own sun is, or from Earth, is Kepler-16? And could you just characterize again the colors of the light that one would get from these 2 stars, as best we can tell?
Kepler-16 system is 200 light years from Earth. And the bright star is kind of orange. It's more orange than the sun. And the little star is red. It's very red. So that's an example of another thing to be considered when you talk about habitable planets is what is the color of the light? Is it color that plants can use to photosynthesize and so on? So yeah, they're both smaller. One's 69% the mass of the sun and one is only 20% the mass of the sun. So together they even weigh less than the sun.
Okay, I don't believe we have any more questions on the phone. Any more questions here at Ames Research Center?
Yes, I'm Jeff Scargill again. I noticed in the artist's rendition the star, the the brighter star is pictured as an active star. Is that based on specific information, or is that just an example of industrial light and magic?
Yeah, both. It is indeed an active star. The flares and the prominences and so on. When you look at the color of a star, you can look at something called the calcium emission lines. And those give you how much star spot activity the star is undergoing. And the calcium emission from Kepler-16A is huge. So indeed, it's a very star spot active.
But you can also see the star spots in the light curve, can't you?
Well, yes. You can also see the star spots in the light curve as little dips. When I showed the actual light curve, I don't know if you noticed, it wasn't just a line, it was these little variations. And those variations are the 35-day period of Kepler-16a. So I might add that the smaller component is the smallest normal star, main sequence star, that's been measured to date. So it's also really interesting to the people who do stellar models. You know, Kepler-16 is a lab for about half a dozen fields to get to work on. It's all sorts of things, from planet formation to stellar models. It's a very interesting lab, instruction kit.
Okay, thank you. Question here at the front.
Hi, April Gage from NASA Ames Research Center. Do you have a sense of the temperature of the planet?
It's about the temperature in the outside of the atmosphere of the planet is about 170 to 200 K. So it's a really nippy day in Antarctica, or a kind of a nippy day on Mars kind of temperature. So even though its orbit is almost identical to that of Venus in eccentricity, it's more circular than Earth's orbit. It's better aligned with the eclipsing binary than the planets in our solar system are aligned. It's quite an amazing system, but it is nevertheless just outside the habitable zone. If it had a moon with a nice greenhouse gas going on, I think we could push it. But we're looking for moons now around it. Nothing yet.
Thank you. We have one more question on our phone bridge. Let's go to that.
Good afternoon. I'm Diane Sabeja from Reforma Journal, and I'd like to know more about the temperature of the stars.
More about, could you repeat the question?
Yes, I'd like to know more about the temperature of the stars.
Oh, okay. Yes, the orange star is about 700 or so degrees cooler than the sun, and I would say that the red star is a couple thousand degrees cooler than the sun. So the two stars are much cooler, and they're not as bright, of course, as the sun. So that even though Kepler-16 is is basically in a Venus orbit, it gets more like the sunshine that Mars would get, a little bit less even.
Okay, thank you. Any more questions here at Ames? Okay, not seeing any. I'm going to conclude today's news conference. For more information about NASA's Kepler mission, please visit us on the web at www.nasa.gov/Kepler, and may the force be with you. Thank you.